Okay. So, thank you, Vincent, for the introduction. Thanks to the organizers for inviting me to give a presentation here. It's my pleasure to also attend the second edition of this workshop. I already attended the first one and gave a very similar talk, also kind of introductory talk 2 years ago. And actually, when I was invited again by Vincent, I thought, okay, this time I will speak about something different, so more recent developments and stuff we did in the recent years. But Vincent, he said, no, you give an introduction. Yeah? So we negotiated a little bit, and after a while, he convinced me that an introduction, of course, would make sense to start the workshop with, and this is why I will again start with a kind of introductory presentation here, although it's at least a little bit adapted, so it's not exactly the same presentation I gave 2 years ago. So the topic is preference learning, machine learning meets MCDA, and I would agree with Vincent that this is, I hope, somehow in the core of what this workshop is about. So my presentation consists of essentially 3 main building blocks. I will start with a very short introduction to the field of preference learning as how it has been developing inside the machine learning community in the recent years. Then I will make a couple of remarks about how machine learning, at least from my perspective, machine learning compares with what people in the MCDA community are doing. And then in the end, I will spend some time talking about what I call here multi-criteria preference learning. It's actually the very first time I'm using that term. I'm not yet convinced that it's a really good term, but we may maybe discuss after my presentation whether or not this is a good terminology. So let's start talking about preferences. Preferences nowadays play a very important role in many applications of computer science and modern information technology, more or less obviously in fields like computational advertising, recommender systems, computer games, and so on. But sometimes also in fields where it's maybe a little bit less obvious, like, for example, personalized medicine, where people are interested in finding medication or therapies that are specifically tailored for individual patients. So here you should maybe not take the term preference literally, but nevertheless the problem is also somehow to personalize alternatives at hand, to maybe rank them from what appears to be most suitable to what appears to be least suitable, and so on. So there are many application fields in which preferences nowadays play a very important role. And there is, of course, also a big commercial interest. So just to give you an example, recently Amazon filed a new patent on what they call anticipatory shipping. And the idea of that patent is somehow to deliver you the product even before you ordered it. Yeah? So that is roughly the idea. Of course, not delivering directly to your home. That would be a little bit too much. But at least, say, deliver to a delivery center close to your home, so that if you order the product, indeed, it will be there very quickly. And what you need, of course, to do that is to somehow have an idea of what are the preferences of people, depending on the region they live in, and so on, and then make predictions about what people are going to order. Preference information really abounds, so people express preferences a lot, especially, of course, on the internet. You find preferences in every form. For example, very informally, people just write text about a product, like a book on machine learning, for example, what they like, what they dislike. Or they give ratings, for instance, on an ordinal scale, typically from 1 star to 5 stars. Or even on a numerical scale, like, for example, on this tomato meter here. So you can give a rating from 0 to 100, which supposed to be a kind of numerical cardinal quality measure. So this is how preferences are expressed in a more or less explicit way, but preferences can also be expressed in a more implicit way, just by looking at what people are doing and how they are behaving. So, for example, if somebody Googles for a name like Daniel Bayer, this is a German colleague of mine, then Google will give such a hit list here, a ranking of websites. And then if you see here on the website, there is not only the professor Daniel Bayer, this is the second one here, but there is also a football player with the same name. Yeah? And whenever there is a football player and a professor with the same name, it appears that the football player is ranked first and the professor second. Seems to me, at least. Yeah. Maybe this is a little bit subjective, but it has to do with preferences, of course, yeah, with preferences of people. So most of the time, it seems people are more interested in the football players than in the professors. Anyway, if now that person clicks on the second link and not on the first one, then, of course, this is some indication that that person is perhaps more interested in the professor than in the football player, and perhaps in general more interested in science than in sports. It's just a guess. So what we collect in this way is, of course, potentially very big data, but also very noisy data. And I am emphasizing this point here because I think this is exactly not the type of data that MCDA people are typically working with. Yeah? They are working with small but well-engineered data, which is not noisy. And this is exactly the opposite of that. Anyway, so against the background of the availability of such large amounts of data of that type, the field of preference learning has recently emerged as a new subfield of machine learning. And preference learning mainly deals with the learning of preference models from observed, revealed, or automatically extracted preference data. And these models, they are typically used for predictive purposes, so for predicting preferences in a new situation that you have not encountered so far, or for new people that you have not seen so far, etc. So this is what preference learning is about. Preference learning is a relatively active field, so we have done lots of work on that in the recent years, but other people too. Personally, for instance, I have given a couple of tutorials already on the topic, some of them together with my colleague Johannes Fürnkranz from Darmstadt Technical University, with whom I also co-edited a book on preference learning a couple of years ago. This is an edited book, but nevertheless it tries to give also a relatively good introduction to the field. And we also guest edited a number of special issues in some journals. So you see that this is quite an active field nowadays. There have also been a couple of workshops organized on preference learning and also related topics in the recent years. So some people in this room, I think, also attended our recent DAX2 seminar on preference learning, the beginning of this year. By the end of this year, so directly after the DA2PL workshop this month, next month, there will be also a very interesting workshop at NIPS on the analysis of rank data. Yeah, Greg will also be there, so we'll jointly attend the workshop too. So you see, there is a lot going on in this field of preference learning. And what is really nice about this field, I think, at least personally, is that this is a very interdisciplinary field. So it somehow grew out of initiatives within machine learning, but nevertheless there are many connection points, obviously, to other areas, to other research fields. So for instance, to economics, the decision science, social science, MCDA, operations research. This is one direction, I think, which is especially also emphasized here in this workshop. Then, of course, to applied fields like information retrieval, recommender systems, yeah, where preferences of people are playing a very important role. And then, of course, also to different subfields of applied mathematics like statistics, optimization, graph theory, and so on. So There are many connection points to other fields, to other research areas, and this is, I think, what makes preference learning also a very interesting research topic in itself. So, preferences, I think my examples already showed this. Preferences can be expressed in many different ways. For example, binary versus graded, you can just say what you like and what you dislike, or you can give preference ratings on a more fine granular scale. Preferences can be expressed in an absolute or relative way, so you can assess a single choice alternative, or you can compare competing alternatives with each other. They can be expressed explicitly or implicitly. We already seen examples of that type. They can be expressed in a structured or unstructured way, for example, rating on a utility scale versus just expressing an opinion in free text. Preferences can refer to single users, or they may refer to multiple users at the same time. They can be single-dimensional or multi-dimensional, etc., etc. So preferences can be expressed and represented in many different ways. And as you may imagine, against the background of that many ways of representing preferences, there is a wide spectrum of different preference learning problems that people already looked at. Just to give you an idea, I will very briefly explain about two different types of learning problems that are actually well known in the literature, just to show you the differences between them so that you get an idea of this wide spectrum of problems I was mentioning. The one which is nowadays known as object ranking starts with training information in the form of pairwise comparisons between alternatives, between objects. This is why it's called object ranking. And typically these alternatives are represented in terms of feature vectors of a fixed length. Yeah, so every object is described in terms of a number of attributes or a number of features. And these feature vectors, they may represent any type of object, for example, cars or books or whatever you would like to compare or rank. And then the goal, the task of the learner is to induce a ranking function from these examples, which again might be noisy and contain mistakes. The task is to induce a ranking function, and the ranking function is a function that accepts as an input any set of new objects, potentially objects you have never seen before, and then provides as an output a ranking in the form of a total order of these objects. So for example, the function takes as input a set of new books and then provides a ranking of the books. And the ranking hopefully is in a good order, whatever that means. I mean, this has to be specified. I will come to this point later on in terms of a proper metric, in terms of a proper loss function. But anyway, the idea is to provide a ranking that is somehow in agreement with the preferences of the person for whom that ranking is actually predicted. Another problem you're probably all well aware of is called collaborative filtering. So here you start with a kind of user product matrix where on every row corresponds to a user, every column corresponds to a product, for example, books sold by Amazon. And then this matrix here is partly filled with ratings, for example, again on a 1 to a certain number of stars scale. So for some users, you know, and for some users and some products, you have information about how much that user likes the product. And then the problem is to somehow fill the matrix, yeah, the empty cells in the matrix to make a prediction of the ratings inside these cells, or perhaps at least for a single user, you may want to predict how much the user likes the different products. And these two problems already have a number of differences I would like to point out. So, for example, regarding the description of alternatives. In object ranking, the alternatives are described in terms of properties, in terms of a feature vector. In collaborative filtering, at least in the standard form, in the simple form, they don't have any properties. They are just described in terms of an identifier, a number, which is meaningless from a learning point of view. The representation of preferences in object ranking is relative, so you compare pairs of alternatives. In collaborative filtering, the ratings are given on an absolute scale. In object ranking, what we are interested in is predictions in the form of rankings, whereas in collaborative filtering, the predictions are given in terms of estimated utility degrees. In object ranking typically refers to a single user, or at least say homogeneous class of users, because the rankings we predict are not contextualized, whereas in collaborative filtering, this is a setting that naturally refers to many users at the same time. So you already see a number of important differences between these two types of preference learning problems. So here is an overview, a table I made a while ago with a number of different problems that have been studied inside machine learning, different types of preference learning problems and their characteristics. Yeah? I'm not going through this table now, it will take me too much time. This is just to show you, yeah? So many problems have already been studied, and these problems really are distinguished by different types of characteristics and properties. Okay, so far this was my very brief introduction to the field of preference learning. The second thing I would like to do in this talk is to compare a little bit these two fields of machine learning on the one side and decision science. I'm still not exactly sure how to call these people all the time. Decision aid, decision analysis, multi-criteria decision aid, decision support, and so on. So there are many names. It's a bit puzzling, but I use the term MCDA here. I think this is not wrong. So otherwise, please correct me. You can feel free to correct me online. Yeah. So machine learning, the core of machine learning is actually about generalization. So what we are mainly interested in machine learning is to generalize beyond the given set of observations we made. So for example, simple binary classification problem, we are given a set of examples, some positive, some negative, some red and some blue. And from these examples, we are interested in inducing a general, say, theory expressed in terms of a model, like, for example, this quadratic discriminant function here, which is a general model in the sense that it provides a new prediction for any new instance we may encounter in this instance space here. So a learning algorithm here actually realizes a mapping from samples to models. So it's a mapping from a sample space to a model space. It assigns a model to every set of observations we made via a process of induction. So inductive inference, this is what machine learning mainly is about. To specify a machine learning problem in a proper way, at least, say, a supervised machine learning problem. There are other types of machine learning problems I will briefly comment on later. We need a couple of things. So first, for example, we have to make clear what kind of training data is offered to our learning algorithm. So what actually is our learning algorithm supposed to learn from? The second thing we have to think about is what type of model are we actually interested in? So what is our learning algorithm supposed to induce? In supervised learning, typically we are interested in learning a kind of mapping from an instance space X to an output space Y. So we would like to have a model H that makes contextualized predictions that are contextualized by an instance description, an X, and then makes a prediction which is an element from an output space Y. In binary classification, the output space is just positive, negative, but this space might be arbitrarily complex in principle. And then in machine learning, we always have this idea there is some ground truth out there which we somehow would like to predict, that we would come close to. And this is why we need to have an idea of what is the nature of that ground truth and how is a model assessed. So how are our predictions assessed? What is a good prediction? What is a less good prediction? And in machine learning, what we are typically using for that purpose is a loss function. Christoph will talk about that in much more detail in his presentation. A loss function, which is such a mapping L that compares two elements of the output space, a prediction and a ground truth, and assigns a kind of penalty for that. So if we predict y and the ground truth is y star, then there is a penalty for making that prediction if the ground truth is given by y star. This is a loss function. And what we are interested in typically is to find a model, to learn a model that has a low risk, where the risk is defined as the expected loss that we suffer from when applying that model, where the expectation is taken with respect to a joint probability measure on the input-output space, which is a model of our data generating process. So P of xy is a probability of observing output y in the context x. And of course, that probability measure is not known. Otherwise, there would not be a learning problem. So this is the risk, and typically what people in machine learning are interested in is finding a risk minimizing model based on the training data available. Of course, there are other criteria too. So for example, like the complexity of a model that might be practically relevant. Typically, we would like to have we would prefer a simple model over a more complex model and so on. But so far, at least, machine learning is very much focused on prediction accuracy, which is a good or a bad thing, something to discuss about. So here is an example, just to give you an example, again, in the realm of preference learning. The problem of label ranking consists of learning models that map instances that might be, again, described in terms of a feature vector, for example, to total orders over a fixed set of alternatives or labels. So here you see a first example where the output space is a little bit more complex and consists of all total orders over a given set of alternatives. So for example, we might be interested in predicting a ranking over a set of journals. So there are 4 journals, yeah? And we are interested in information of the type, yeah, mark, for example, described in terms of a feature vector, whatever that means. I don't know, I just took some numbers here. 52 years old, and yeah, published 324 papers, etc., etc. So can basically mean anything. But the important part of the information here is that Mark prefers the eJOR journal to information science, to fuzzy sets and systems, to the artificial intelligence journal. I don't know whether this is true. It's just a guess. But suppose this is the type of information we are interested in. So where this preference information here, once again, let me make this point. You should not always take this preference literally. So it can be any relation. So it can mean, in terms of the semantics, for example, likes more, yes, but it can also mean reads more or publishes more in, etc. So it can be any kind of order relation we are interested in. Now, the training information in preference learning just consists of pairwise comparisons, because typically we cannot expect to have a full ranking over all choice alternatives from all the observations we make. So we assume training information just to be given in terms of instances together with pairwise comparisons. So this person here, for example, likes A more than B and C more than D. But other than that, we don't know anything. So training information is given in terms of pairwise comparisons. We don't demand full rankings. From this training information, we would like to induce a label ranker, and the label ranker is a function that accepts a new instance as an input, like for example Alexis here. Yeah? I deliberately took this picture, not the one from his website, because he looks so angry on his website. Where is Alexis? He's not yet here, right? Okay. So here he looks much more friendly. Yeah? So we take Alexis. We don't know anything about his preferences, and we would like to predict them. For example, in terms of a ranking, which can be expressed as a permutation over the 4 choice alternatives we have. Yeah? And then there is a ground truth. So, for example, Alexis, after we made our prediction, reveals his true preferences. Then what we need is a loss function. And there are many different loss functions we may apply. For example, we may look at the candle loss, which just counts the number of pairwise inversions. So the pairs of journals, for example, we rank in an incorrect way. Yeah? This loss function is related to the to the well-known candle Rancor relation, which is just a linear transformation of that loss function. So this is what we, for example, could use in order to evaluate, to assess a prediction. Now, in general, machine learning, the machine learning scenario, at least the simple one of supervised learning I was just commenting on, looks as follows. So what we typically start with is an assumption about a data generating process that we consider as the ground truth, yeah, which is somehow out there that we somehow would like to target. We assume to be given typically a kind of population. So, for example, all people on the world, or the French population, or whatever, which corresponds to the probability space on which we are working in a statistical terminology. We also assume that there is a kind of stochastic process that is eventually responsible for generating the data we observe. And I made this point already. Typically, we don't assume that there is a deterministic dependency between inputs and outputs, and data we may observe might be corrupted by noise. So this data generating process produces the data we observe, and from this data, very much like in inferential statistics, we are interested from that data we are interested in generating a model about this data generating process, and this is done by virtue of a learning algorithm. So we apply a learning algorithm to the data, and then we get a model, and the model somehow tries to capture, at least to some extent, parts of this data generating process. So what is important here is, it's important with regard to this distinction I would like to make to this MCDA field, is that the model typically refers to an entire population of individuals, typically not to a single individual, but a population. Knowing this model allows for making good predictions on average. So typically these models are intended to perform well on average, not specifically tailored for a single person, but on average over the population. The dependency tried to be captured by the model is not deterministic. I already mentioned this. And this is due to different reasons. For example, due to the fact that there is an aggregation effect. The same people, for example, might be mapped to the same feature vector, in which case we cannot distinguish them, even if they have different preferences. The observations we make are corrupted by noise, etc. And these are all reasons for why this dependency is not assumed to be a deterministic one. The scenario, okay, yeah, a couple of further remarks. This assumption about this ground truth, so the assumption that there is a ground truth out there, typically allows for deriving theoretical results on the learning algorithm, like different types of guarantees of how it will perform, which are of the type, for example, if the data generating process is such that there is a linear dependency plus noise term which has a Gaussian distribution, then our learning algorithm is consistent in the sense that if the sample size goes to infinity, yeah, we will come as close as we want to the deterministic dependency and so on, guarantees of that type that people in machine learning are very much interested in. The second thing, this focus on predictive accuracy allows for doing simple empirical comparisons. And you will hardly find a machine learning paper without such an empirical part where you apply your new learning algorithm to a set of benchmark data and measure the prediction accuracy empirically. So this is very simple to do. This is very simple to do, and this is another thing that machine learning people are very keen on. So theoretical results, guarantees on your learning algorithm, plus empirical comparison. Now the situation in MCDA looks a little bit different. Now, if I'm saying anything wrong, please correct me. Yeah? So I don't want to say anything wrong about this MCDA field, but this is at least my impression of my perception of that field. So in MCDA, typically we don't look at the whole population, but at a single individual. So we are interested in finding a model of the preferences for a specific person, for example. Not necessarily a person, but say one individual. In the beginning, this individual, I mean, the goal is the individual, the person, for example, wants to get a clear idea of his or her preferences. And in the beginning, there is not very much. So the person, for example, is very unclear about his or her own preferences. There is a decision analyst that works with that individual in a kind of interactive process. For example, by asking questions, queries about the preferences. And the person is step-by-step revealing preferences. And in this way, the picture about, say, the preferences of the people, of the person, become more and more clear. So step-by-step, yeah, the person gets more clear about what are my own preferences and, for example, what is the reasonable ranking of the choice alternatives I am confronted with. Yeah. So if you compare this to the machine learning scenario, there are a number of very important differences. So one I already mentioned, typically there is a focus on a single user, not on a population. Second, the process is typically very interactive. Yeah, it's not that the ground truth generates the data and then we are given the data and we are doing something with this. No, this is a very interactive process between the decision analyst and the person, the individual. Inconsistencies can be discovered and corrected within this process, this interactive process between the decision maker and the individual. So if something does not fit, for example, the decision analyst may ask back, so do you really think you prefer A to B? And then the person may think about it and maybe make a correction or change his or her mind. The process, and this is now very important, this is why I started with this empty circle here in the beginning, and this is also why I needed some time to actually understand, that we make a very different assumption here in machine learning. The process is in a sense a constructive one, in the sense that the preferences of the people are constructed during the process, and there is no assumption of any kind of ground truth. So it's not that you compare a true versus an estimated model of the preferences of the individual. So it's something like construction versus induction. So it's not that we assume that there are the true preferences of the person, and in the end we come up with a kind of approximation of it, and then we can compare the two. So MCDA people typically do not make this assumption that there is some ground truth out there. And this is why, also this is one reason for why the evaluation or the assessment of the result of such a process is very difficult to make. You cannot easily compare, like in machine learning. Yeah. So this can be, again, a good or a bad thing. We had quite a discussion about this also at our DA2PL' seminar, where the machine learning people somehow said, okay, but in MCDA, now I exaggerate a little bit, but you can do anything, and in the end, you cannot really say that what you propose is not a good method because you cannot really falsify. Yeah? in the end, what counts is the happiness of the user, the decision maker, which is a little bit difficult to measure, at least if you don't make real experiments with real people, with real users. We in machine learning, we have a really hard measure. We can really easily assess our models. This is to some extent true, but on the other side, we also have to admit that in machine learning, this, say, hard evaluation is a little bit oversimplified, right? Because it's actually not true that all what counts in practice is the prediction accuracy of a model. Actually, what counts is much more. And if we are just looking at accuracy, then the picture is a little bit oversimplified. I mean, we also have to, I think, we have to agree on that. So yeah, there are certainly pros and cons of having such a simple way of evaluating models you learn. I would also like to point out that for different reasons, this comparison I made is a little bit black and white. It's a little bit oversimplified too. So first, for example, there are, of course, other settings in machine learning. Not only this simple supervised setting, simple setting of supervised learning I was sketching, but also things like semi and unsupervised learning, active learning, online learning, reinforcement learning, etc. Likewise, there are many different types of, say, procedures that MCDA people have been looking at. And then, perhaps even more importantly, there are really things that already are a little bit in between the two. And this is actually, I think, where we should further look at. So, for example, there are Bayesian approaches to this way of preference elicitation that MCDA people are interested in. Work on this has, for example, been done by Paolo and Greg Boutelier. They studied preference elicitation in a Bayesian, in a stochastic setting, doing some kind of active learning, for example, using this notion of expected value of information. So here, this is kind of combination of the two settings. It's preference elicitation in the sense of MCDA, but at the same time, the methods that are used are more from the machine learning field, Bayesian inference, and the setting is not deterministic, but again, it's stochastic. Likewise, for example, other people like Thorsten Joachims, for instance, they recently started work on what he calls machine learning with humans in the loop, yeah? Which is also very much geared toward interaction. So how can a continuously learning system benefit from interaction with the user, and what is the best way of interaction, and how do you extract training information from the user interaction, and so on. This is also somehow in between these two scenarios I was sketching. So once again, of course, this is a little bit oversimplified. So at our DAX2 seminar, we had a long discussion about the comparison of the fields, and we came up with a relatively big table in which we compare preference learning with MCDA. There is, by the way, also a third column, which is conjoint analysis. We also had people from conjoint analysis at the seminar. And conjoint analysis, once again, it's something very close to preference learning. It's done by people more from statistics and especially in marketing. Yeah? It's a very widely applied method. But for the time, for the purpose of this workshop, you can just ignore the third column here. Yeah? Anyway, we compared these two fields with respect to a number of different criteria. And I will now go very quickly through this table because I don't have time to discuss every row in detail. But if you are interested, we may, of course, continue discussion later. So the problem focus in preference learning is more on the predictions we make. In MCDA, it's more that we focus on the user or the decision maker. User interaction in preference learning, it's typically not so much emphasized, although there are things like active learning and so on. In MCDA, it's very much emphasized. So the process is constructive, and there is always user feedback, and the user is always somehow in the loop. The learning domain in preference learning, it's more that it's about the population. The goal is to generalize across individuals. In MCDA, we are given a single user, typically. The representation of alternatives in machine learning, they are typically feature-based, but they can also be structured. But the the big difference to MCDA is that in machine learning we are very often working with very long feature vectors, or say containing features of low level features, whereas in MCDA the features are typically much less, but they are very well engineered. So typically the people in MCDA, they call these attributes criteria, and they are typically very well engineered, have a well semantics. Yeah? The representation of users in machine learning, it's typically feature-based too. In MCDA, often there are no really, I mean, the features of the, or attributes of the users actually don't play a role. The preference information in machine learning, it's often holistic in the sense that we compare two complete alternatives. For example, I like A more than B, without looking at specific aspects of these alternatives. And in MCDA, the preference information is typically much more rich. You can not just give a holistic comparison, but you can also say, I like A more than B, but, for example, the color of A actually could be improved a little bit, and so on. So the nature of the data, as said already, in machine learning, it's typically noisy, probabilistic setting. In MCDA, the data is typically assumed to be consistent, and if it's not consistent, it's somehow made consistent. So the table goes on, yeah, you see. The models and model assumptions. In machine learning, we typically start with relatively weak assumptions about the model, and this weak assumption is somehow compensated by the big amounts of data we ideally have at hand. In MCDA, we typically start with very strong assumptions, perhaps even axiomatically founded ones. The model interpretation and what do we actually expect of the model. In machine learning, we are mainly interested in predictive accuracy. MCDA is a mainly constructive process. And the goal is somehow to convince with a model in terms of in the sense of giving a good explanation for the decision maker, for example, for why he should prefer A as the best alternative and not B, and so on. Data in machine learning, it's massively available, not always accessible, but in principle, there is much data out there. In MCDA, the access to data is not that easy, and there is no big repository of benchmark data and so on. So the data volume in machine learning is possibly very large, but noisy, and in MCDA it's typically quite small data that we are working with. Validation success criteria, I already mentioned. Accuracy metrics typically used in machine learning. They are determined by internal validation on the data, at least estimates thereof. And in MCDA, it's that we want to make the user happy somehow. And this is, of course, more difficult to measure. Computational aspects, scalability to big data is very critical and important in machine learning nowadays. In MCDA, it's less critical because, yeah, data is often not that big. Application domains in machine learning are very broad, but typically not very safety critical. Like e-commerce, for example, it doesn't make it's not actually that important that we always recommend the best book to a person or whatever. And often machine learning applications are used for kind of automated decisions, whereas MCDA also is applied to relatively safety critical applications and often kind of one-shot decision-making problems. So once again, this comparison is a little bit oversimplified, but anyway, I think it's at least good enough to somehow have a global picture of how these fields may distinguish, but what is more important, actually, of how we may learn from each other and what we may contribute, and how the two fields may cross-fertilize each other. Okay. So coming to the last part of my presentation, I would actually like to speak a little bit about what I call multi-criteria preference learning. So what do I mean actually by that term? By multi-criteria preference learning here, I refer to what I also earlier called the model-based approach to preference learning. And what I mean by this is preference learning methods that proceed from specific assumptions about the type of preference models, structures, rankings, to be learned from a machine learning point of view. These are typically models that come with a very strong representation bias, very strong learning bias, but also generative approaches making specific assumptions about the data generating process, like, for example, probabilistic models on rankings like the Mellows model and the Plackett-Luce model, or Bayesian methods. So these are models making strong model assumptions, and these can be contrasted with, say, empirical loss minimization on generic function classes, like things like, for example, rank SVM doing or rank boost, where the class of functions, the class of models, however you want to call them, we are fitting is a very generic class, like linear functions or kernelized functions, or convex combinations of linear functions and boosting and so on. So a little bit exaggerated, we may say, we distinguish here just fitting functions, what we are doing here, versus learning interpretable and somehow cognitively plausible decision models. So this is the distinction I would like to make here. Examples of this latter class of models are, for instance, the Choquet integral that I'm going to speak a bit more about on the next slides. But also things like, for example, lexicographic orders or CP networks and related networks like generalized additive independence networks. Also models like, for example, the majority rule models, MR sort, etc. These are things, for example, that Marc and Vincent with their students recently worked about. Or models, for instance, that are inspired by decision-making procedures like TOPSIS that we recently started also to work on, etc. So the idea here somehow is to combine work in MCDA on the one side on preference modeling with learning technology on the side of machine learning. And for me, this is one very important way of how the two fields might be combined. This is one, say, topic that I personally consider really within the intersection of these two fields. Yeah? Machine learning people somehow benefit from what the MCDA people have been doing on the side of preference modeling. Sometimes it's indeed very important that you have a model that you can easily interpret and from which you can extract important information. So just to give you an example, we recently fitted a model to the ECML PKDD 2014 data. I had access to the data because I was a PC co-chair, so I could extract the data. And the data actually that we fitted here is about the overall recommendations of the reviewers and the final decision of acceptance or rejection of a paper. So what we fitted here is an over operator, yeah, to the data, and the model is the model we ended up with using logistic regression to make the model fit is the following. So the log odds ratio here between the probability of acceptance or rejections of a paper given the reviewer ratings is a linear function of this type here, where x min is the worst recommendation of one of the three reviewers. X medium here is the middle one, the second best, and X max is the best recommendation. Yeah. So we sort the reviewer recommendations in increasing order of their recommendation, and then we fit this model here. And this model, just as a side remark, it performs quite well in terms of prediction accuracy. So we obtain a cross-validated accuracy of 92.5%, which you can interpret as you like. You can interpret it as we as a PC co-chairs are quite predictable people in a sense, yeah. But you can also interpret it as the reviewers did a good job in the sense that most of the time we agree with what they say. sometimes not. Yeah, but anyway. Now, what is actually interesting is to look at these coefficients here, I think, and also at the threshold. The threshold surprisingly well fits 0.5. I mean, it's not tuned, it's really estimated. So we really threshold at 0.5. This over of x here is between 0 and 1. Yeah, it's located between 0 and 1. So 0.5 is a reasonable threshold. And what is interesting now is to look at these coefficients here. The highest is given to the second best reviewer recommendation, which somehow suggests that there is a tendency toward averaging. Indeed, I mean, there is a tendency toward averaging the 3 reviewer recommendations. But the x min has also a significantly higher weight than the x max. So the bad reviewer recommendations somehow count more than the good ones. And this is what perfectly fits experience. If you have to make decisions about the papers, typically the critical reviews are also the more substantial ones. And if you have a selective conference like ECML, then typically you only accept papers that don't have any bad recommendation. Yeah? And so this model somehow agrees well with expectation in a sense. But the thing is, you can nicely interpret it. And this model I am showing you here with this over operator is a special case, actually, of what I'm going to talk about now, namely the Choquet integral. So the over operator is a special case of the Choquet integral, the discrete Choquet integral, defined on a set of criteria C1 to Cm, which I mentioned already play the role of what we call attributes or features in machine learning. And the discrete Choquet integral, with respect to what is called a capacity here, the mu is a non-monotone measure from C to the unit interval, is defined in this way here. It's always very difficult and time-consuming to explain this expression. And since we are going to have a complete talk about this given by Michel, I won't speak about this here. So I can just refer to Michel, who is a big expert on the Choquet integral. And I won't talk about this further here, which would take too much time anyway. Let me just mention that so what the Choquet integral actually is a generalization of a standard integral toward non-monotone, non-additive measures. Yeah? So the mu here is not necessarily additive, and this allows one to capture interactions between the features. So the feature contributions or the contributions of the different criteria are not necessarily independent of each other. And this is a very nice thing. And this is also the reason why the discrete Choquet integral is a very flexible aggregation operator that captures the minimum operator, the maximum as special cases, but also things like the simple weighted average and this over operator I was showing earlier. One important remark, because I will take advantage of this later on, is that the Choquet integral can also be expressed equivalently in terms of the Möbius transform mu, the Möbius transform, the standard Möbius transform of this set function mu, this measure, this capacity mu. The technical details are not so important now. We have been working on, the use of the Choquet integral within a machine learning context in the recent years. And we advocate the Choquet integral especially as a model that nicely combines the learning of monotone models, so monotonicity, nonlinearity, and interpretability. So it has these, somehow nicely combines these 3 features. What I just said, these features in machine learning, they typically play the role of what is called criteria in MCDA. But what is also used, I'm mentioning this because I will come back to this a little bit later on, is that we turn these, raw features into normalized features that somehow can be interpreted as local utility degrees via a process of normalization. This is important because the Choquet integral somehow makes the assumption that the data, the measurements are somehow commensurable, so they must be somehow comparable and on the same scale, which typically is taken as the unit interval. So these UI values here is what you can think of as the evaluations of the criteria made by a function f that we are then actually integrating. And this is why we understand this value delivered by the Choquet integral applied to such a feature vector as the value of that function applied to the different features. So the idea is we apply the Choquet integral to somehow combine these local utility degrees into a global utility degree. We have been using the Choquet integral in different learning contexts, like ranking, for example, where we start from training information given in the form of comparisons between objects, but also for what is called ordinal classification in machine learning, or sorting in the MCDA field, where you assign every instance to a category, an ordered set of categories. And then the goal is to find a Choquet integral that in some sense agrees well with these categorizations we have seen as training information. A special case of this is just binary classification, where we only have two categories, the good one and the bad one. And this is what I'm going to focus on now. I think I don't have too much time left, so this is why I'm going to hurry up a little bit. One important point here, what I said earlier, is that we cannot use the Choquet integral, say, directly as it is, because we are always making this assumption that there is some, say, stochastic process behind. The data we observe is not, might be corrupted by noise. And this is why we somehow have to, say, wrap the Choquet integral into a kind of stochastic process. Once we did this, we can use estimation techniques like maximum likelihood estimation and so on, so statistical inference techniques, which can be contrasted with things that are typically used by MCDA people like linear programming, etc. So how does this actually process look like? We consider the decision making as a two-step procedure. The first is that given an instance x, we somehow combine the normalized utility degrees into one overall utility, which is called u here. And then the decision is made, the binary decision now for the sake of simplicity, by thresholding this utility at a threshold beta. So this means that if you exceed the threshold, you say it's good or positive. If you are below the threshold, you say it's bad or negative. So we have a step function here. This is still deterministic, and now the stochastic component comes into play by replacing this, say, deterministic step function by a logistic or noisy response model that looks like this here. So this is a logistic transformation, actually, where we have, in addition to the beta, the threshold, we have another parameter gamma, which somehow is responsible for what I call here the precision of the model. And what this equation here is showing is actually, it's modeling the probability of saying positive or good, yeah, as a function of the value delivered by the Choquet integral. And it looks like this. We simply replace the step function by a smooth logistic function here. And the gamma controls how steep actually this function is, the gradient of the function. For gamma going to infinity, it converges toward the step function. For gamma equals 0, we have a random decision maker that just makes choices at random. For intermediate values of gamma, we are somehow in between. Okay, if you can give me, yeah, okay. So with this decision process, we end up with a model that we recently introduced in the literature under the name Choquistic regression. It's a merger of two terms, Choquet and logistic. Yeah? That's why it's called Choquistic regression. And it's actually a generalization of logistic regression, in the sense that if the Choquet integral here is just weighted average, a special case, then we recover logistic regression as a special case. But the advantage is that our model here is, of course, much more expressive. We developed this in a couple of papers with a doctoral student of mine in the recent years. Now, how do we fit models? How do we do model estimation? So given a set of training data, for example, in the form of, here is an instance, and I will. Here is an instance, and this is the correct output for the instance. Then, given our stochastic model, we can look at the likelihood function, which is just the probability of observing that data, given a set of parameters, where the set of parameters is here the two parameters beta and gamma, plus the parameter specifying the capacity, so, or the equivalently the Möbius transform of the capacity mu. And what you can do then is maximum likelihood estimation. So you maximize the likelihood, or equivalently you minimize the negative log likelihood, which is written here. The problem is that we have to do this under a couple of constraints that assure the monotonicity of the capacity we are learning, the measure mu. And this is a quite nasty thing, because the number, if you do it in a naive way, the number of constraints you end up with is exponential in the number of criteria. So this means the whole procedure is computationally very expensive. It's not only computationally expensive, it's also that from a machine learning point of view, you may say, okay, a model with that number, that high number of degrees of freedom is very prone to overfitting, and this is certainly true. We have shown this more formally by computing the VC dimension of this thresholded Choquet integral, and we found that the VC dimension of the Choquet integral grows at least as fast as 2 to the m over square root m, where m is the number of criteria we have. So this is indeed an issue from a machine learning point of view. The good thing is that if you restrict yourself to k additive measures, then the VC dimension is of the order m to the k. So we can use the k, the degree of additivity of the underlying capacity, also for capacity control, by the way, in a double sense. Yeah. In a first step, some local utility functions are defined on the different criteria, and they somehow transform the observed values into a utility degree. And then in a second step, these utility degrees are aggregated into an overall global utility degree. Here we use the Choquet integral as an aggregation function. What people in, say, machine learning have been focusing on so far is learning this aggregation function here, assuming the local utility functions to be somehow given or predefined. Yeah? Now, there is, of course, a big challenge to simultaneously learn the aggregation and the local utility functions, because there is an influence, yeah, on both sides. The local utility functions influence the aggregation and the other way around. I am mentioning this because Christophe, where is he? Yeah, he will give a talk on this issue. He will present a joint work that we recently did on that topic, a first step toward simultaneously learning the aggregation and the utility function. By the way, there is an interesting question of identifiability. Is the model defined in that way still identifiable, in the sense that you can simultaneously identify the parameters of the local utility functions and the aggregation? Okay, so I will skip this about this Topsis-like model and just conclude, because I'm already over time. Preference learning, this is my standard, say, advertisement slide, is an interesting topic for many reasons. I don't want to repeat this here because, yeah, I'm running a bit out of time. I would just like to make two more points. First, there is already a couple of established methods in the field, but the field is still developing, still growing. Recently, for example, into the direction of online preference learning. In my group, we did work on preference-based bandit algorithms and stuff like this, preference-based reinforcement learning, etc. And very important for this workshop here, I think there are really many links between preference learning on the one side and decision aid, multi-criteria decision aid on the other side. And most of them are still to be explored. So I have given one example here, what I called multi-criteria preference learning, but there are many other things that one may look at. And this is what this workshop, I think, is really good for. So here's a number of selected references, and that's all from my side, and I'm sorry for having taken a bit too much time. Thank you.